Let's do chemistry past paper 2010 MCQ 3. So I'll read the question. A certain salt dissolves in water and gives a colored solution. When diluted NaOH is added to this solution, a pale green precipitate is formed. When NH4OH is added to this precipitate, it dissolves, forming a blue solution. The cation presence in the salt is, so they have given 5 answers as usual. So we can see the answers, right? So the answers are cobalt 2 plus, nickel 2 plus, Fe 2 plus, and Fe 3 plus, and chromium 3 plus. So from this we can understand that this is something to do with inorganic chemistry, and especially and more precisely it is something to do with D block elements. All right, so first of all, let's get to know why these, this kind of, these 3D block elements, shows us different colors. Okay, I mean they form different colors. So this question is about, they are, putting some kind of salt in a solution, they are putting into NaOH and they are putting into NH4OH, and finally they get some kind of color. So it's about it. So let's, talk about the color. So how these, complex, these how these metals, transition metals, form colored compounds. All right, so for that we have to analyze these thing into 3 different sets of, title. Okay, first of all, we have to understand the 3D blocks and the transition elements. Okay, that is the first title. And the second title is, we have to understand the complex ion. Okay, how these transition metals form complex ion. Okay, so that is the part 2, that is the title 2. And in the third part, okay, in the third title, we are going to look at how this complex ion form colors. Basically we have 3 titles, so let's go. All right, let's talk about the D block elements. Okay, so the D block position in the periodic table consists of element in the group of 3 to 12. In this group, the D orbitals are filled progressively. So the elements which are present between the S and the P block elements in the modern periodic table are called the transition elements. So transition elements usually have partly filled, D orbitals. Please note that the transition elements usually have partly filled D orbitals. So actually the zinc also from D block, but the D orbital of zinc is fully filled, so we cannot consider zinc as a transition metal. So transition metal must have a partly filled D orbital, then only we can call it as transition element. So D block elements are different and transition metals are different. So actually these transition metals or transition elements fall under the D block element category. Okay, so not all the D block elements are transition elements, but every transition elements are D block elements. You have to note that. So one exception is zinc. Zinc is a D block element, but it's not a transition element. So I have told you that in the transition elements, the last electron usually enters the D orbitals. Okay, the last electron usually enters the D orbitals. Okay, So we have to, we have to check the FBAO, principle here. So just, refresh the FBAO principle. So here we should talk about this FBAO principle, the building block principle. Okay, so let's talk about it so we can, just revise it and we can make it understand. So once we understand this FBAO principle, then we can understand this total, scenario very clearly. So FBAO principle dictates that the manner in which electrons are filled in the atomic orbitals of an atom in its ground state. It states that the electrons are filled into atomic orbitals in the increasing order of orbital energy level. Note this point, increasing order of the orbital energy level. So according to the FBAO principle, the available atomic orbitals with lowest energy levels are occupied before those with high energy levels. So let's do some practice in order to understand this FBAO principle. Let's do the electron configuration for vanadium. So vanadium's electron configuration is its argon's configuration, so argon's electrons configuration, and 3d3 4s2. So this is the configuration. So we can write like this. So the first electron will go to the 1s. So the first electron would go to the 1s and the second also go to the 1s, because in one shell you can fit 2 electrons. You should fit 2 electrons. So here 2 is done. So the third one is going to the second s and the fourth one also going to the second s. Then the other one is going to 2p, 1 2 and 3, and another 1 2 3 completed, 2p completed. Then the next electron would go to the 3s, 1, the other one 2, it's completed, and the next one will go to the 3p. Okay, 1 2 3 4 5 6, 3p completed. Then the other electrons will go to 4s. Okay, so that is 1 2, 4 is completed, and we have remaining with, how many electrons we are remaining with. So we are remaining with 3 electrons. Okay, now the 3 last final electrons will go to the 3d 1, and the next this one, and the next this one. So now we have partly filled orbital. Okay, actually this 3d orbital could accommodate another 7 electrons, because each shell can accommodate 2 electrons. So 5 into 2, that is 10. So this total 3d orbital could accommodate 10 electrons, but here we have only 3. So this is partially filled, partially filled. And even if you add another 2 electrons, it will become like this, 5. But you may think like, yeah, it's fully filled. No, 5 shells there and 5 electrons fully filled. No, you have to add another 5 to fully fill this whole shell. Okay, whole these 3d orbitals. Then only it'll be filled. Okay, you need to put another 5. That's mean total 10. Alright, so we are partly filled. So this is what we called as transition metals. All the transition metals are like this, at least in their ground state, if not at least in their ion state. So this is how we decide whether it's a transition element or else non-transition element. So actually we have studied this transition metal. So this transition metal has a unique ability to form complexes, ion complexes. So what is ion complex? So ion complex, or you can call it by complex ion. So a complex ion has a metal ion at its center with a number of other molecules or ions surrounding it. So these can be considered to be attached to the central ion by coordinative or dative covalent bonds. Okay, so dative covalent bonds. Okay, not the covalent bond, coordinative covalent bond. Okay, you have to note that. So the molecules or the ions surrounding this central metal ion are called ligands. The molecules or ions surrounding the central metal ion are called ligands. Let's say a nickel complex ion. So we have nickel 2 plus in the middle, in the center, and this nickel 2 plus is a metal ion, okay, that is attached to 6 NH3 molecules, and we have another counter ion here, that is 2Cl minus. So altogether we have 6 NH3 and 2Cl minus. We have altogether 8 ligands. Okay, so this nickel is connected with 8 ligands. So this is what we call it as a complex ion. So this transition metals complex ion has an ability to show you colors. It has this ability. It can form colors. Okay, it can form colored compounds. Okay, so why do transition metals form colored compounds? So transition elements have 3D orbitals with the same energy level. However, when molecules, for example ligands, in our case that is NH3 plus this Cl minus, form dative covalence bond with the metal ion. Okay, in our example that is nickel, the metal ion mean nickel 2 plus. So the electron repulsion causes 3D orbitals to split into lower and high energy level. So we will get 2 higher energy levels and 3 lower energy levels. So this is the lower energy level and this is the higher energy level. It is because of the repulsion. So the energy required to cause an electron to jump from a lower 3D orbital to a higher 3D orbital corresponds to a certain wavelength of visible light. So this wavelength is absorbed while the other wavelengths of light passes through, which gives the compound its color. So here we have orbital. So these are the lower energy orbitals. So we have 3 orbitals, 3 shells. Okay, those are the lower energy orbitals, and these are the high energy orbitals. So we have 2 shells. Here you could see that the d orbital is split into 2 orbitals. The one is lower level energy orbital, the other one is high level energy orbital. So if a lower level electrons, this could be this or this or this, wants to go up to the higher energy orbital, to this orbital, then it needs some energy. So if you want to go to Kandy from Colombo, your vehicle needs petrol, right? So at least if you want to go to Kandy by walk from Colombo, you need energy. You need food to eat. Then only you'll get the energy. Then only you can walk. Okay. So same thing here. If this electron wants to go to this higher orbital, then it needs energy. So this electron gets this energy from the light wave. Okay, so from there are so many wavelengths in the light, in the white light. Okay, so each wavelength, corresponding to a different level of frequency. Frequency mean energy. So if an electrons want to move from here to there, there's a gap, right? There's a space, there's a distance. So this distance would vary to each complex ion. So it depends on the central metal ion and the oxidation number of the ion and the ligands. Okay, so these are the factors which would affect this distance. So based on this distance only, the electrons would require energy. For example, if this distance is very small, then the electron would require minimal energy. If this distance is huge and it needs huge energy, a lot of energy. So from the wavelength, from the white light, we have different wavelength. So each wavelength corresponds to a different frequency. So the lower wavelengths correspond to higher energy. So if these electrons need high energy, it will absorb this highest frequency. So what is the highest frequency here? So in the white light, the highest frequency goes to what? Goes to violet. So violet has the highest frequency and the shortest wavelength. So red has the least frequency. So based on that, if this electron needs high energy, it will absorb this one, or less than that, it will absorb indigo, or less than that blue, or less than that yellow, or this or this or this. So if it needs least energy, then it'll go for this red. So that's how it works here. So if the gap is so I already mentioned you, the gap, the distance is affected by three factors. The first is the type of that metal, the central metal. So for copper, the distance would be different. For nickel, the distance would be different. For ion, the ion mean Fe, the distance would be different. And for vanadium, the distance would be different. So it will change accordingly. So the distance will change accordingly. So the type of ion, the central ion, would definitely affect this. That is one thing. And the second thing is the oxidation number. For some metals, for example, let's take iron, that's mean Fe, iron. So for iron has two oxidation number. One is Fe2 plus and Fe3 plus. So these two oxidation number would affect the distance. For Fe2 plus, it would be smaller, and Fe3 plus would be higher. So it may affect. Okay, and the last one is the ligand. Because of the ligand, the repulsion, the repulsion rate or the repulsion force may vary. Okay, for some ligand, the repulsion force would be smaller, and for some it would be much higher. So based on that, this distance would vary. Okay, so if the electrons want to go from this orbital to that orbital, from low energy to the high energy orbital, then it needs to consume some energy. How it consumes energy is, it will get the energy from the white light. So it needs a specific energy that would correspond to this distance. So this electron would absorb that energy only. So if that electron absorbs that energy, then the energy corresponding to that frequency, and that frequency corresponding to that wavelength, and that wavelength is corresponding to that color, would be absorbed. once it is absorbed, okay, by this electron, then you will not see this color. So what will you see is, you will see the complementary color of this one. So we have a color wheel for this. So the complementary color for red is actually green. This color, the complementary color is this. For this, the complementary color is this. So if the electron absorbs this color, and you will see this color. If the electron absorbs this color, you will see this color, something like that. So that's how you see. So we have three factors, so those would affect the distance between the high and low energy orbitals. So if this distance changes and the energy requirement changes, if the energy requirement changes, then the frequency changes. If the frequency changes, then the wavelength changes. If the wavelength changes, then the color would change. You have to understand that. This is the very important thing. So that's why we are seeing different colors for different complex, because of the distance between that orbitals. So you have to understand it very clearly. So now you understood how these colors are formed by this complex ion. Okay, let's go to this question and let's do this. So let's answer this question. So we have just seen how these colored complex are formed. Okay, so based on that, the transition elements, okay, they have this unique ability, unique feature to form colored complex. So you don't need to break your head, okay, in order to find the answer. Okay, you don't need to use qualitative analysis for this. It's actually a chart is given in your resource book. You can check that chart. Okay, so this is that chart actually. So metal complexes and colors. There are some genius students who perform this qualitative analysis to find the color. This is actually a very straightforward question. You don't need to do qualitative analysis for this this question. There's a chart, you look at the chart, you find the answer. So what they are saying in the question is, so first they dissolve in the water and it gives a colored solution, but they didn't mention the color. Okay, so first they dissolved in the water, right? Then they added diluted NaOH to this solution. So pale green precipitate is formed. So let's check, because we have ligands and the metals, the transition metals, and the corresponding colors as well. So we can check that. It's very easy. No need to do qualitative analysis and all. So first they have given cobalt, CO2 plus. Let's check the cobalt. Cobalt 2 plus, here, it's here. Cobalt is here. So what is the ligand? The first ligand is H2O, but we don't know the color. So let's move for this OH. So they have put diluted NaOH. So it turned pale green precipitate. So here, see, with that it's pink precipitate. So this is not the answer. And they put NH4OH. So actually NH4OH contains NH3. Okay, so the next ligand is NH3. For that it should give a blue color. Okay, blue color solution. So cobalt give yellowish brown color solution. So this is not the right answer. Okay, so cobalt is not the right answer. Cobalt is not the right answer. Then nickel 2 plus. Okay, let's check nickel. Nickel is there. So with the water it's green, but they didn't give the color in the question. And with NaOH, diluted NaOH, this gives green precipitate. See, so this matches with the question. Okay, and for NH3, okay, it gives blue, same solution. it gives blue. It's 2 matching with the question. So the answer would be Ni. Okay, nickel. Okay, nickel 2 plus. Let's check other, other remaining answers as well. So for Fe2 plus, let's check. So Fe2 plus with water it gives pale green, but we don't know the color because they haven't given the color in that question. And for NaOH it gives a dirty green precipitate. So it's dirty green, not the pale green, but we aren't sure about it. Okay, and for NH4OH, that's mean NH3, it gives the dirty green, precipitate, the same color. But in the question, they are mentioning about the blue color. So this is not the answer. And they have given Fe3 plus as well. So this is for Fe2 plus and this is for Fe3 plus. So here, with water it gives yellow brown color, and with NaOH it gives reddish brown color. Here it's eliminated. Okay, because this is wrong. Okay, because in the question they say that pale green color. Okay, and for NH3, okay, that's for NH3, that's mean NH4OH. Okay, this gives reddish brown. Here it fails. So Fe2 plus or Fe3 plus is not the right answer. And the final one is chromium 3 plus. Let's check the chromium 3 plus. So the chromium 3 plus gives violet color with water, with H2O. Okay, and with NaOH it gives blue green precipitate. It's blue green, not the pale green, but we aren't sure about what the blue green is. So let's move to this. So with NH3, so NH4OH contains NH3, so this is fine. So with that it gives blue green same precipitate. So in that question they are precisely mentioning about a blue solution, so this is wrong. So chromium 3 plus also wrong. So Fe3 plus wrong, Fe2 plus wrong. The only correct answer is nickel 2 plus. So this is how you do this question.